Okay, so you guys have your exam tomorrow, right? And everyone's super excited, ready for the exam? Okay, so hopefully after today you'll feel better going into the exam. Maybe you know what to expect. It's always kind of hard with, first time seeing my teaching style, my exam style. So to kind of give you an idea, it looks like my quizzes. So it's about 4 quizzes. So we've already given 3. So if you think of just another quiz on top of that, sit down and take it, that would be very similar to your exam. So last Thursday I passed out this study guide, and it just kind of has concepts that would potentially show up on the exam. Today I want to kind of elaborate on some of that, like definitely see a problem like this and go through it. Maybe you see a problem like this. And if you have any questions, I can pull up problems from the book, from Wiley, from lecture, or just out of thin air, and hopefully that will give you some reassurance of what will be on this exam. So today our plan is to review, and first I want to talk about Chapter 0, which is really kind of the Are You Ready for Calculus? So, find the formula for the inverse function. Generally, in the past, I've always put a find the formula for the inverse function on the first exam. We've done 5 examples of that. Are you ready for calculus? There was 3 examples. You can see here. The find the inverse function. And then on the quiz, the first quiz I gave you, there showed up 2 examples. And they're similar to the Are You Ready for Calculus, slightly different. Not much, but do you guys feel okay about finding the inverse of the function? Right? Rewrite it, things like that. The definition of trig functions together with their domain and range, that doesn't come up directly in this section. However, when we get to the limit and continuity, you need to make sure that the function exists at that point. So tangent doesn't exist at minus pi over 2 and pi over 2. So it's not going to be continuous there. So that really comes up later on to know that where their domains and range lies. Because if I say, is tangent continuous? Find the interval in which tangent is continuous on. It might be a multiple choice type question. If I have pi over 2 over there, you cannot click that. You cannot choose that choice because tangent is undefined at pi over 2. Right? Tangent sine over cosine, cosine 0 at pi over 2. So there's multiple ways to go about thinking about it. That really comes up later on, not anything directly. I won't ask what's the domain and range of tangent. But we'll be in a problem potentially with continuity. Algebraic properties of logs listed in theorem 0.5.2. The sum of logs, the difference of logs, the product of logs. If you think of Wiley's, you guys did the homework over this. I might have an expanded log and ask you to simplify it into 1 log. I might have 1 log and ask you to expand it. So we didn't really do an example. We didn't spend too much time on this. So I'm going to do an example in class of the log question that potentially might show up. So if I give you expand the log into simpler logs. So might be more elegant than this, but I don't want to take the time to write out the whole sentence. So if I give you log base a of the 7th root of x plus 3 squared over x cubed minus 8. So there's a lot going on in this example. And I want to expand that out. So the first thing I want to do, I can write this as log base a of x plus 3 squared over x cubed minus 8. I can write this to the 1/7 power, right? The 7th root of something is that something to the 1/7 power. So I know log base a of x to the r can be written as r log base a of x. Do you guys remember that? So I can simplify this to 1/7 log base A of x plus 3 squared over x cubed minus 8. And then recall that if I have log base A of x over y, I can write that as log base A of x minus log base A of y. So if I apply that in this expression, I have 1/7 log base A of x plus 3 squared minus log base A of x cubed minus 8. I can simplify this more by bringing down the 2. Here, I can factor this. X cubed minus 8, you guys, difference of cubes. So I can factor it as x minus 2 times x squared plus 2x plus 4. Right? Remember SOAP? Same, opposite, always positive as far as the signs go. I'm going to drop down one more. So I have 2 log of x plus 3 minus the quantity log base A of x minus 2 plus log base A of x squared plus 2x plus 4. And this is as simplified as it can get. There's no other simplification you can do. One problem that I've seen in the past on this is students don't know when to stop. Like, oh, well, I'm adding 2, so I'm going to then multiply them, or various crazy things. So be careful. You're done here. There's not anything else you can do. There's no more simplification. You could distribute the negative and drop the brackets here, but if you don't, you're not going to lose points. If you do something like log of base A, there's an A there, sorry, of x times log base A of 3, or log base A of x times 3, all those you're going to lose points for. That's not correct. So don't do that. Know when to stop. So the one on Wiley was a little more straightforward. There was less things to do, but I could give you something like log base A of x times y times z over p. So you'd be able to expand that out as log base A of x plus log base A of y plus log base A of z minus log base A of p. All right. If I squared this, then I would have a 2 here. Are you guys comfortable with messing with logs? Question?
So you wouldn't have to put like parentheses around the whole log x, y, and z, because the whole thing is being divided by p. That doesn't matter.
Yeah, you wouldn't need parentheses here, simply because if you drop them, it is not going to change.
It's just addition. Okay.
Yeah. So I mean, really, you could break it up that it's log base A. If this times this times this divided by this. If there was more than 1 in the denominator, I would need to distribute the negative. This 2?
Yeah.
This 2 said if p was squared.
So that's a 2 right there. Okay.
Yeah. Sorry, kind of looks like a z.
Yeah.
I try to always write my z's with a line so they don't look like 2s. So.
Can you move it up a little bit, please?
Any other questions with that? So that's covering really this review pretty. So we talked about the inverse. We talked about the trig functions and their domains, where that comes up. Did an example of the logarithmic functions, the sum, the difference, the product, things like that. If you look on this theorem 0.5.2, you can see how that is applied. And then trig problems from the Are You Ready for Calculus quiz. So if you think of, and it's actually not the quiz, it's just Are You Ready for Calculus. We didn't do any trig problems on our quiz, but So if you think of the Are You Ready for Calculus, an example of a trig problem that could show up would be a problem like this, where you have to know something about the quadrants. All students take calculus. Everything's positive in the first quadrant. Calculus. Students, meaning sine and its reciprocal, cosecant, is the only thing positive in the second quadrant. The third quadrant, cosine and its reciprocal, secant, is the only thing positive in this quadrant. I said tangent, sorry. Calculus, C, cosine, its reciprocal is the fourth quadrant. Tangent is the third quadrant. Tangent and cotangent. So if I give you sine of some angle, that gives you the relationship. And then I say that sine is negative and cosine is negative. That only happens in the third quadrant. So then tangent is going to be minus 1 over minus 3. Question?
Could you explain that little trick?
So if I don't know if I've written this in class before, right? All students take calculus. If you write that, this is saying all the trig functions are positive in the first quadrant. Sine and its reciprocal is positive in the second. Tangent and its reciprocal is positive in the third, and cosine and its reciprocal. Everything else is negative in the other quadrants. So all students take calculus.
And then how did we know how to, I always get confused
Mhm.
with when you're given sine equals 1 over square root of 10. How do you know where to make the triangle?
Because sine is opposite over hypotenuse. I know to make it in the third quadrant because sine is negative and cosine is negative. That only happens in the third quadrant, right? Because it would happen in, that only happens in the third quadrant. So then I know to draw the angle in the third quadrant. Then I get the relationship, it's minus 1 over square root of 10. The hypotenuse is never negative. It's always positive. So here the x component's negative and the y component's negative. So when I go to tangent, it's positive because it's x over y. Right? Negative over negative, so it's always positive.
And you were able to determine the 3 and the 1 from the only two roots that'll add up to 10.
Yes. Yes, because I use Pythagorean's theorem. A squared plus b squared equals c squared. So
Okay. Negative 1 over 10 or excuse me, negative 1 over the square root of 10 is not some place that's specific on the units.
no. I don't know what this angle is. If it was a 1, 2 square root of 3 triangle, then I could say, okay, it's a 30, 60, 90 degree triangle, and then I could come up with some angle. But it's not asking for the angle. It's asking for what tangent of the angle is. So let's look at an example, I think. Let's look at how we would go about, this is a little bit different form, but along the same idea. So find the exact value of tangent of secant inverse of 9 over 4. So there's a lot going on here. But I'm looking for some angle that if I take secant inverse of that, I get 9 over 4. Or if I take secant of that, I get 9 over 4. And then I plug that angle into tangent to see what I end up with. So not along the exact same lines, but still a trig type problem. So this is saying that there's some angle that secant of some angle is 9 over 4. Secant's 1 over cosine, right? Cosine inverse only exists in the first and second quadrant, if you think about graphing it. So basically I have this angle, secant's 1 over cosine. So if I know secant of theta is 9 over 4, then I know cosine is adjacent over hypotenuse, so this is hypotenuse over adjacent, so this is 9 over 4, right? Maybe my reasoning didn't click, but if you could get to that on your own.
You said, so if it's 1 over, if secant is 1 over cosine, isn't cosine 4 over 9?
Cosine would be 4 over 9. So it would be adjacent over hypotenuse.
And because that's positive, it has to be in the first one.
Correct. Yeah, so there's a lot of stuff coming together here, right? But yeah. So I could have just say, I want to just always deal with sine, cosine, or tangent. I could write this as tangent of 1 over cosine inverse of x. Well, 9 over 4. 9 over 4. Well, I want to say, yeah, so this actually, let me think of how I want to write this. Yeah. I could write it as tangent of cosine inverse of 4 over 9. Did I say 1 over that? Because secant is 1 over cosine. Yeah, so it'd be 1 over that.
Well, then it would be flipped again.
No, because think of this. This is different. This means the inverse, not 1 over it. It's not saying 1 over secant. Secant's 1 over cosine, right?
You say arc cosine instead of.
You can, yeah. It's just depending on where this is coming from. I could write it as tangent of arc secant of 9 over 4. So that would be tangent of, tangent of arc of 1 over cosine of 9 over 4, 1 over cosine of 4 over 9. Yeah, it doesn't mean flip it. There's a difference between sine of x to the negative 1 power and sine of the inverse of x. Question?
What is that? What does that mean?
What mean? The arc? Arc means the inverse function. And that means, the inverse function means you're finding an angle that satisfies the relationship. Because generally they're saying, okay, what's sine of the angle? It's a relationship. But the inverse function is saying, what is the angle that gives you this relationship? That's what the inverse function means. So this is different than this. This doesn't equal this. This would be, 1 over sine, which would be cosecant. And this is saying what angle gives you, what angle, when I plug it in sine, gives me x. Question?
I don't understand something. Tan 1 over cos inverse of 4 over 9. I don't get it.
Let me see if I want to put it 1 over.
Because, I don't know, I think.
Okay, so maybe don't try to rewrite it in terms of cosine inverse. Just think secant's 1 over cosine. Cosine's adjacent over hypotenuse, so secant's hypotenuse over adjacent. Does everyone feel comfortable with that? Question?
Does the inverse of secant have the same restrictions, 0 to pi, or is it?
Of secant, it's 0 to pi. Cosecant would be minus pi over 2 to pi over 2, because cosecant sine. And
So they have the same,
they don't have those same restrictions. So think of the graph of sine.
but like
This-
cosine and secant have the same restrictions, and sine and cosecant have the same restrictions? Like they're inverse?
Okay, so the restriction is on the inverse because I have to limit the domain to be 1 to 1. So if I graph sine, I have this graph, right? I pick the domain to be minus pi over 2 to pi over 2. So the restrictions are going to be in the first and the fourth quadrant. Minus pi over 2 to pi over 2. But cosine is 0 to pi because I have cosine looks like this. And so whoever decided on the bounds to make it 1 to 1, right, because it goes like this, they picked 0 to pi, so that turns out to be the first and the second quadrant.
But will
So
secant have those same,
the reason why I pick this, so the inverse exists. So the inverse, so secant inverse of x is 1 over cosine, or sorry, secant of x is 1 over cosine, right? So if I limit cosine to be from 0 to pi, wait, not cosine, secant, I think, because that was going to 0. Yeah, so the inverse, inverse cosine, so cosine inverse of x. Oh, sorry, cosine inverse of x, this is only my input can only be in the first or the second quadrant. Sine, my input can only be in the minus pi over 2 to pi over 2. So yeah, if I want to rewrite it, I can rewrite it as tangent of cosine inverse of 4 over 9. There's no 1 over that. Because I'm flipping the relationship to the hypotenuse in the adjacent, or hypotenuse over adjacent, adjacent over hypotenuse, depending if I'm dealing with cosine or secant. The inverse is saying I'm looking for an angle that gives me this relationship. The angle that gives me the relationship of cosine of 4 over 9 is going to be the same angle that gives me the relationship to secant of 9 over 4. Right? So you can write it like this. If it's given to you like this, you can just set it up. So this is going to give me the same thing. I'm looking for this angle. This angle gives me a relationship. When I take secant of this angle, I get 9 over 4. This same angle, when I take cosine, I get 4 over 9. So this is an angle. So what am I going to get when I take tangent of this angle? So I need to find this value. So this would be 4 squared plus y squared equals 9 squared, which is 81. So 81 minus 16, 65. So this becomes the square root of 65. So now what is going to be tangent of this angle? Very good. Square root of 65 over 4.
Is that the answer?
The answer is square root of 65 over 4. So right, if I have any relationship, let's go to look at some of the books and where these come up. 1 point is in chapter 0, inverse trig functions. I don't know if we did too many. Sine inverse. Those are proving identities. So let's just think of another one. Let's say I do sine of cosine inverse of 2. 1/2, sorry, 1/2. So let's look at this problem. I'm looking for the sine of an angle that when I plug that angle in cosine, I get 1 over 2. Right? So what this is saying is there's cosine of some angle is 1 over 2. So the inverse function means. I'm looking for this angle, so cosine, it's positive, so I know it's in the first quadrant, because it's either in the first or the second quadrant. Sine's either in the first or the fourth quadrant. So cosine would be 1. All students take calculus. That's if it's positive or negative. It's the inverse, so it only exists in the first or the second. Everything's positive in the first quadrant. So if it's positive, it's in the first quadrant. Cosine only exists in the first and the second quadrant. Cosine inverse only exists in the first and second quadrant. Sine inverse only exists in the first and the fourth quadrant. So if sine inverse is negative, it's in the fourth quadrant. If cosine inverse is negative, it's in the second quadrant. Okay, so cosine of theta, cosine, I'll get rid of this. Cosine's adjacent over hypotenuse, so it's 1, 2. So make this go away right now, sorry. So I have to find this angle, so I have 1 squared plus y squared is 4. So y is square root of 3. So this is my angle. So what is going to be sine of my angle? Square root of 3 over 2. And that would be your answer. So drawing a picture on these is worth quite a bit. So you start on the inside, and in your setting up that relationship of theta. If it's sine, it's opposite over hypotenuse. If it's cosine, it's adjacent over hypotenuse. And then once you have the triangle, you complete the missing piece by the Pythagorean theorem. And then if it's tangent, it asks you your relationship. If it's sine, cosine, you do whatever that is. Opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent. If it's cotangent, cosine, cosecant, you know how to deal with those, right? So maybe you should have started with a little bit easier example than the one I gave previous. But does that make sense now? Right? So I'm looking for some angle that has this relationship. When I plug in cosine, I get 1 over 2. Once I have that picture, I look at that picture and take the sine of that angle. Okay, so it's not on the quiz, but the trig problem. So your trig problem will come from something similar to what you did on the Are You Ready for Calculus, where I give you the relationship of sine or cosine or tangent or whatever, and then I tell you, basically give you all the information to know what quadrant it is, and then ask you for a trig function of that angle, of that theta. 1.1, limits and intuitive approach. We've done 2 examples on quizzes of how to take a limit, basically from a graph. Our first quiz, I gave you this example. I asked limit on the right, limit on the left, limit at the point, versus the value of the function. So make sure you understand how that works. And the same thing on quiz number 2. I gave you a little bit more involved problem, but still the same approach. The limit on the right, the limit on the left, the value of the function at the point, things like that. Question?
What is the problems on Wiley where we had to create our own graph? And I don't know if it was this section, but with the discontinuity, where the 3 dots didn't match up with the actual.
Yeah.
And I still not do this.
Like here?
I just guessed, yeah.
So, I mean, I might give you this graph and ask you about the limit. Do you understand the limit as x goes to -1 from the right goes to 1?
Yes.
And then the limit at x goes to 0 goes to 1? And the limit as x goes to 1 from the left goes to 1? But the value of the function at these 3 points are 0?
Can you show the actual equation? Where does it say that?
There's no equation. It's just you're graphing a function that satisfies these conditions. These conditions are saying that at -1, 0, 1 is 0. So you better have a solid point on those points.
Yeah, so whenever I see the picture, I can identify the information.
Yeah.
But when I
Given
see
the information,
I
you can't put it in the picture. There's more than one correct answer here. Multiple things you can do. Your graph has to be on the domain here. So you need a point from -1 to 1. Everything in between has to be defined. But the way you go about it can be any way you go about it. Wiley gives you this graph, so you put it in the right spot. But if you're doing it on paper, could you make a graph that looks similar to this that has all these conditions? And that's it's almost easier when you get to make it up on your own, because you can say, okay, I need a point here, here, and here. I have to have a point here. Well, then my function has to be approaching 1 on this side. But it can do anything at once, as long as it's approaching 1. It could be a straight line, yes. It could be a straight line as long as this is open circle. Right? It could be a straight line. Question?
So for those, it's like the limit as x goes to -1 from the right equals 1. The limit as x goes to 0 equals 1.
Yes.
Like, is that what it's saying?
Yeah,
So
it's-
like each of them, if they just put it in one thing, but
Yes.
they're actually like
Yeah, it's
separate.
saying this equals 1, this equals 1, and this equals 1.
Okay.
So they all equal each other and they equal 1. But it's not saying, I mean, if you just look at
I
this,
think
it's kind of
that, like,
confusing.
the way they write it is just confusing.
So yeah, if there's one on the exam, potentially look different than the setup, but emphasize, yeah, it's saying that the limit at these 3 places equals 1. So I think we've done quite a few examples on 1.1. 1.2, computing limits. So, piecewise defined function, if you look at the quizzes, I think we've done examples of this one multiple times. If you have a constant over something going to 0, that goes to infinity, right? If it's going to 0 from the right, if it's positive, it's going to infinity. If you have a constant over something going to 0 but it's negative, it goes to minus infinity, right? 1 over something going to 0 goes to infinity. It's an important concept because that will be in a couple of the limit ones. So, right? So I almost want to write this up. So 1 over something going, I'm going to put a constant instead of 1. Going to 0 is infinity. Now, if the constant's negative and you're going to 0 and it's negative, they're going to cancel, right? And you're going to get infinity. If the constant's negative and you're going to 0 positive, it's minus infinity. So you have to be a little careful, right? You can think of an example if I say the limit as x approaches minus 7 from the left of x over x plus 7, right? So the top's going to minus 7. So minus 7 from the left of minus 7, that's like minus 7.01, right? If I add that to 7, I get a positive number. Sorry, I get a negative number, right? Because I have a negative 0.01 left. So this is negative, but going to 0, which would be positive infinity. So you, go ahead.
I thought that these were always going to be less than 0 because they're coming from the left side.
Be careful when it's negative, right? Because on the left side of minus 7, it's less than negative 7, but it's a bigger number. Absolute value is bigger, right? Negative 7.01 is on the left side of 0. It's less than minus 7. You owe someone more money, right?
Sure.
So it's less than minus 7. But when I plug it in here, I get that it's going to a negative number. But let's look at, so that's why I always think about these problems. Write them out. Don't just say, oh, if it's going to the right, it's going to be positive infinity. If it's going to the left, it's going to be minus infinity. Think about what you're doing here, because on negatives, it takes some time, right?
So they can't. So the negative on the top and the bottom cancel each other out.
Correct.
Okay. Now I can. Okay.
Right, so this is negative going to 0. So yeah, that negative on top and negative on bottom cancel each other out. So be careful with things like that. But you should know 1 over something going to 0, or a constant over something going to 0 goes to infinity. I'm going to put plus and minus down here, plus and minus, but you would never write plus or minus infinity. This is just what your answer is, either plus infinity or minus infinity. Maybe put something like minus infinity, plus infinity. Those are your options for a constant over something going to 0. A constant over something going to infinity, what does that go to? 0, right? This is going to 0. This is going to infinity, which is what your limit equals. Okay, so quiz 2 had examples from 1.2. If you think of a piecewise defined function, I ask you for the limit on the right. You need to show me you're plugging in the point to the right side of the function. The right side, the function that's defined on the right side. The limit on the left, you plug it into the function that's defined on the left side of your x. If I ask you for the limit at the point, you have to check if the limit on the right and the limit on the left equal each other, then the limit exists. If they don't, the limit doesn't exist. Question? On 1.3? Number 9 on 1.3? This one? Okay, so I'm going to infinity, right? So I look at the highest power, right, of x, because that's what I care about. The in behavior, I care about the highest power. I have minus 3 infinity cubed. Infinity to the 5th power. Infinity to the 5th power is infinity. What's infinity times minus 3? Negative infinity. Does that make sense?
go over that rule because I don't see the reasoning behind it.
Okay, so in 1.3, okay, so does this cover 1.3? Okay, so 1.2, does anyone have any questions on 1.2? Pretty straightforward, right? Limits. 1.3 has to do with, finding limits of polynomials. In behavior, so the limit is going to infinity. In college algebra, you did horizontal asymptotes, which are similar. In this example, I take the highest power of x in the numerator and in the denominator, and I end up with a negative number times x. X is going to infinity. So a negative times infinity is minus infinity. This example, my highest power of x is in my denominator. I have a negative number. So I have a negative number of something going to infinity. A constant over something going to infinity goes to 0. Okay. If I look at just taking limits of polynomials, so this is 1.3. In behavior, a polynomial matches that of its highest degree term. Right? So if I'm taking the polynomial that has a fifth degree and plugging in infinity, that goes to infinity. If I'm plugging in minus infinity, it goes to minus infinity. I have to be careful with the coefficient, right? So let's look at some examples. 1.3. What would be the limit as x goes to positive infinity of 2x cubed minus 100 x squared minus x minus 1? Well, that's going to, the end behavior of a polynomial is going to match the end behavior of its highest term. This is the limit as x goes to positive infinity of 2x cubed, which would be 2 times infinity cubed, which would just be infinity, right? Question?
If it's negative infinity and it's to an odd coefficient, would it,
It's an odd power,
or yeah,
right?
power.
So if I have something like the limit as x goes to minus infinity of 2x cubed plus whatever, it doesn't really matter if it's smaller, right?
It'll be negative.
Yeah, because it's 2 minus infinity cubed. Well, minus infinity cubed would be negative infinity, and 2 times negative infinity would be minus infinity.
And what if the power is 4 or something?
The power is 4, right? The limit as x goes to minus infinity of 2x to the 4 would be 2 minus infinity to the 4th power, which would be 2 times infinity, which would be infinity. So be careful also with the coefficient, because the coefficient can be positive or negative. Right? In polynomials, really it all ends in the end behavior, and if you're in college algebra, if I have a x to the n, where n is even, and a is greater than 0, I have a function that looks like this, where the end behavior is both positive. If n is even and a is less than 0, I have the end behavior that looks like this. If n is odd and a is positive, I have a graph of a function that looks like this. And if a is negative, I have a graph of a function that looks like this. Right? So you can see from the graphs, the end behavior is going to be both positive or both negative anytime the end behavior is x goes to infinity or minus infinity. That's what I mean here. Both positive or both negative. If the highest power is odd, depending on the coefficient of a, it's going to be positive infinity or minus infinity. And they're going to be different from each other. So 1.3, algebraic techniques for dividing numerator and denominator by the highest power. So you can always apply that. The end behavior of trig functions, limits can fail to exist because oscillation. I won't ask you what's the end behavior of sine of x, because it doesn't exist, because there's oscillation there. Right? That's something, potentially to know about in the future. I'll only ever ask you the end behavior of, if you look at 1.3 in this section, it's a good representation. End behavior functions, like this example. If I plug in minus infinity, the end behavior is going to act like highest power of x is in the denominator. So I have a constant over something going to infinity. minus infinity, 0, right? So I get 0 there. Here, this example and this example, oh, not that one. This one, this one. So examples that look like with the square root, that might show up, so know how to evaluate them. Divide top and bottom by the highest power of x in the denominator. So a lot of times you write that as the absolute value, because you can replace the absolute value with the square root of x squared. So then you can put it in the numerator here. Here your answer is going to be square root of 5, but be careful, when x is going to positive infinity, it's pretty easy, because the absolute value of x can be replaced with x. However, when x is going to minus infinity, I think this one's going to minus infinity. This one, you have to be a little bit careful with the absolute value of x is actually replaced with minus x. In this case, you divide top and bottom by x squared, so you don't have to worry about replacing a negative number or not. Here, the horizontal asymptotes, highest power of x in the denominator, so this is going to go to 0. Highest power of x in the numerator, so this is going to go to infinity or minus infinity, depending on if I'm going x going to infinity or x going to minus infinity. And here, what's the limit as x going to infinity? What's it going to approach? 1, right? The a over b.
On the middle one there,
Uh-huh.
can you go back up to the one?
Yeah.
So if it's higher in the numerator than it is in the
Denominator. Then it's going to go to infinity or minus infinity, depending on the polynomial that results.
And thus
Right.
there's no horizontal.
Correct. The horizontal asymptote doesn't exist.
Right.
But the limit would be infinity or minus infinity. That's good. Okay. So, not have too much time left. So, I want to hit some other concepts. 1.5. Oops. 1.5 continuity. Really, this has to do when you give a piecewise defined function. You have to find the value of k that makes the function continuous. We did a couple of examples of that in class. For continuity, the limit on the left has to equal the limit on the right, has to equal the value of the function at the point. So know how to do that types of problems. Continuity of trig, exponential, and inverse functions. 1.6, this would have to do with potentially seeing how do these functions work with each other. So if I'm taking the limit as x goes to infinity of cosine of 1 over x, so you get to see what is 1 over x going to as x goes to infinity? 0. What's cosine of 0? 1. So use your answer there. In this example, what is sine of 0? 0. What's e to the 0 power? 1. So you can see here, if I'm taking the limit as x goes to 0, I have e to the 0 power, e to the 0 is 1. Here, the limit as theta goes to 0 of sine of 3 theta over theta. What would be my answer be? It'd be 3, right? Because I multiply top and bottom by 3. I get sine of 3 theta over 3 theta goes to 1, and I'm left with a 3. This example, 25 is a good one. The limit as theta goes to 0 from the right of sine of theta over theta squared.
1 over x. 1 over theta.
1 over theta, but theta is going to 0. It's going to 0. 1 over something going to 0 from the right, because it's from the right. 1 over something going to 0 from the right, positive infinity, right? So let's just take a minute to write this one up, because I think it would be beneficial. So this is number 25 on 1.6. I'm taking the limit as theta goes to 0 of sine of theta over theta squared. Ooh, that's zoomed in there, but... All right. So I can write this, the limit as theta goes to 0, and it's from the right. So So that's the important thing. I can break up this theta squared to be theta times theta, right? And then I can group this. From the squeeze theorem, I know this goes to 1. So really, I'm looking at the limit as theta goes to 0 from the right of 1 over theta. What's the limit is? This is going to 0, but always positive.
You got a thing on the screen right in the way up there.
Oh, sorry. My zooming. There we go. So this would be 1 over something going to 0, but positive, so that gives me positive infinity. All right? Important concept. 1 over something going to 0 goes to infinity. If I asked you the limit as x goes to 0 of 1 over x. Does not exist. Very good. The reason why it doesn't exist, because the limit as x goes to 0 from the left goes to minus infinity, and the limit as x goes to 0 from the right goes to positive infinity, right? And they don't equal each other.
Do we have to show that to get full points?
No, if you says doesn't exist, that would be fine. But what about the limit as x goes to 0 of 1 over absolute value of x? Good. Positive infinity. Because the limit on the right equals the limit on the left, so the limit at the point exists. Right? The limit on the right would be positive infinity. The limit on the left, the absolute value of a negative number is always positive, so it's positive infinity. Okay, so 1.6, continuity, trig functions, pretty straightforward. No e to the negative infinity goes to 0. E to the infinity goes to infinity, right? Think of that graph. If I take e, so this happens, I guess not really there. Then 2.1 is the last thing in the last 2 minutes. Tangent lines and rates of change. So if I ask you what's the average slope, the slope of the secant line, I'll give you 2 points from A to B. And to find that, you always take, let's see, the average rate of change is always delta y over delta x, right? And if I say from A to B, it's f of b minus f of a, b minus a, right? This is the average rate of change. The instantaneous rate of change is the slope of the tangent line. So there's multiple ways you can go about finding that. You have to find the derivative and plug the point in for the derivative. And if you want to use techniques that we learned in Chapter 2, that's fine. If I give you like x squared and I ask what's the slope at, what's the instantaneous rate of change at 1, the derivative of x squared is 2x, right? So if I plug in 1 to 2x, it's 2. So the slope is 2. The slope of the tangent line is 2. If I ask for the slope of the secant line, you're going to have to plug in 2 points, like from 1 to 5. So it's f of 5 minus f of 1 over 5 minus 1. Anyone have any last minute questions? Last minute? All right, so you're, go ahead.
When you do that, when you plug in the f of 5,
Yeah, you get a number.
then you, okay.
Yeah,
You get like that.
versus a function, yeah. All right, I will see you guys tomorrow. Good luck studying.